today is Thursday. No, it's not. It's Wednesday, October 7th. And we are going to be doing the polygon angle sum theorems today. I am going to go kind of quickly, so you can stop this or have Mr. Farina stop it at any point. It's also up on YouTube, and at that, tell him what the search is so that you can search it on YouTube if you miss something. All right, we're going to start off with what a polygon is. A polygon is a closed plane figure whose sides are made of segments. The plane idea is important because that makes us realize that we're on a flat surface, that we are not going to be three-dimensional. Also, the sides only intersect at their endpoints. Let's look at some examples down here of some figures and determine whether or not they are polygons. This first one, yes, that is a polygon. How about this second one? What do you think?
Is that after the A at like a specific point?
Yes.
Okay.
Sorry, a student just came in to ask me a question. All right, how about this second one? What do you think? Yes, this is not a polygon. Why not? Because it's not closed, it's open here. How about this one, this ice cream cone shape? That is not a polygon because it's got a curved piece here. That's not a segment. How about this star? The remaining two are two stars. One of them is a polygon, one of them is not a polygon. This one right here is not a polygon because this side right here intersects this side right here, not at just its endpoints. It intersects at a bunch of different points. Kind of the sides cross over each other. This star, where those pieces in the middle, if you will, are erased out, this is a polygon. Okay, with these polygons, it's also important to name them. And to name a polygon, we start at any vertex. Another way to think of vertex is a corner. So you start at any corner, then go around the polygon in order. For example, to name this polygon right here, we could start at F, this corner, and go around clockwise, and this would be polygon F, R, I, E, and D. We could also start at, say, N, and this time instead of going clockwise, we could go counterclockwise, which is backwards around. So N, E, I, R, F, D. We could start at E and go counterclockwise. E, I, R, F, D, N. We could even start at E and go clockwise. E, N, D, F, R, I. What's not acceptable is if we zigzag across. If we went F, R, D-I-N-E. So if you zigzag across, that is not an acceptable way to name that polygon. Other important vocabulary here, a diagonal. A diagonal is a segment that joins non-adjacent vertices. A segment that joins non-adjacent vertices. Okay, go into the school supply bags under your desk and grab a ruler. Adjacent means vertices that are next to each other. So non-adjacent are vertices that are not next to each other. So P and U, those are next to each other. P and E are next to each other, but P and R are not next to each other. So those are non-adjacent. There's one diagonal here. There's another diagonal here. And in this case, segment PR and segment EU are diagonals. In this next one over here, we need to talk about diagonals on this one. You are used to seeing diagonals this way, where the sides are kind of running vertically and horizontally, and that diagonal is on a slant. Diagonals do not have to be on a slant. They just connect non-adjacent vertices. So if we look at this pentagon, 5 sides, here's a diagonal right there. RA is a diagonal because it connects non-adjacent vertices. Here's another diagonal. RT is another diagonal. Do you see any more? WT is a diagonal. WE is a diagonal. There's one more diagonal. Who sees it? Yep. EA is the last diagonal here. Okay, we can also talk about different types of polygons. There are convex and concave polygons. That one's convex. This one's concave. The formal definition for convex is that no diagonal has points outside of the polygon. If we look at this, if we draw in diagonals, notice that every single diagonal is inside of the polygon. Okay, there's one more. Oh, there it is. But if we come over here at this concave polygon, the definition is that at least one diagonal has points outside the polygon. And if we look in this one, here's the diagonal right there. If I connect these two vertices, they are not next to each other. So that's a diagonal, but that diagonal is outside of the polygon. of the ways that I remember that this is concave is I think about this as sides bending in. So it's like a cave. You know, you walk into a cave, so here the sides bend in like the entry to a cave. You can use that if you want to, but however it is, you need to be able to tell the difference between convex and concave. Most of our time is spent with convex polygons, and we are going to take a look at this chart and fill out this chart for convex polygons. I am going to go through this kind of quickly, so again, stay with me. If you get stuck, you can go up on YouTube, and you can find this up on YouTube a little bit later. Okay, the polygon with the least number of sides has 3 sides. Picture, this is a triangle. Looks like that. Okay, alright, now, number of diagonals from one vertex. So if I start at one vertex and I try to draw a diagonal, I can't. Everywhere I go from this one vertex, I hit an adjacent vertex. So there are no diagonals from one vertex. How many triangles are there? There's only one. And the sum of the interior angles, you all know, is 180. The next quadrilateral has 4 sides. Rectangle, square, but don't draw one of those. Draw something odd. Maybe something like that. The name of that, it has 4 sides. It's a quadrilateral. Okay, now, number of diagonals from one vertex. Start at one vertex, just one. How many diagonals can you draw? Just one. When I drew that one diagonal, how many triangles did we get? We got 2 triangles. So the sum of the interior angles is 2 of those triangles times 180 each, which is 360. Okay, a 5-sided figure is a pentagon. Let's choose a vertex and the number of diagonals that we can draw from that one vertex is there. That's 2. How many triangles did we create? 3. So all the angles on the inside, 3 times 180, which is 540. A 6-sided figure is a hexagon. Diagonals from one vertex. There are 3 of them. 4 triangles. Hopefully you're starting to see some patterns here. 4 times 180, and I'm going to help you with the arithmetic here. That's 720. Alright, 7-sided figure. Very difficult to draw. We're not going to draw that one here. It is called a septagon or heptagon, depending on the textbook that's used or the context. You can choose whichever one. I would accept both of those. Diagonals from one vertex, clearly following the pattern, there will be 4. Number of triangles created, there will be 5. Sum of the interior angles, 5 times 180, that's 900. Okay, 8-sided figure is an octagon. we're not going to fill the rest of this out. We're going to generate some patterns here in a minute. 9-sided figure is a nonagon. 10, decagon. 11 we really don't talk about. 12 is a dodecagon. Okay, that is not your bell. That was the bell to end my study hall, so if it's getting a little loud in here, it's because they're leaving while I'm recording. If you could hear some whispering in the background, it's because my study hall was whispering while I was recording to you. So they should be leaving here in a minute. Excuse me a minute. Excuse me, guys. Hey, get out. I'm still recording. Goodbye. All right. Now, for other sides beyond these guys, to name them, we'll call them n-sides, and it's called an n-gon. I know it sounds weird, but that's an n-gon. So a 37-sided polygon is called a 37-gon. All right, now what I need you to see is not necessarily this pattern going down here, but this pattern going across. How you can get from the number of sides to the number of diagonals from one vertex. So if you have 3 sides, we have 0 diagonals. 4 sides, we have 1 diagonal. 5 sides, we have 2 diagonals. 6 sides, we have 3 diagonals. Are you all seeing that it's this number of sides minus 3 to get to here? So number of sides minus 3. All right, now kind of forget about this column right here, these 2 columns, and again, go from number of sides to number of triangles created. 3 sides creates 1 triangle. 4 sides creates 2 triangles. 5 sides creates 3 triangles. So what are we doing? Minus 2. So n sides creates n minus 2 triangles. All right, next, how can you get from this column, number of triangles created, to the sum of the angles? Well, it's this column times 180. So down here, this column, n minus 2 times 180. All right, this chart serves 2 purposes. One, to have you associate the number of sides with the name. Yes, you need to know the number of sides and the name. I expect you to know that an 8-sided figure is an octagon. I expect you to know that a decagon has 10 sides. You need to know these. That was one purpose. The other purpose is to have you recognize this pattern so that we could come up with these formulas down here on the bottom. And down here, I'm going to summarize these formulas for you. So if you really didn't see the patterns, don't worry about it. You can get it from here. So these are some important formulas for convex polygons. With n sides. And the first one is the number of diagonals from one vertex is n minus 3. The number of diagonals from one vertex is n minus 3. That's this right here. N minus 3 is the number of diagonals from one vertex. That's still not your bell. Sorry. Okay, the next piece of information is this formula right over here, this n minus 2 times 180. That's the sum of the interior angles is n minus 2 times 180. That's that formula. Okay, These last two formulas I did not do a chart for. You are just going to have to believe me on these, and Mr. Farina can verify. The sum of the exterior angles just one at each vertex is 360 degrees. That's it. The sum of the exteriors is 360. It is not dependent on the number of sides. So whether you have a triangle or an octagon or a dodecagon, the sum of the exterior angles is always 360. In the last formula, again, there's no formula up here in the chart. I am just telling you this. The total number of diagonals from all vertices is n times n minus 3 all over 2. Number of sides times the number of sides minus 3 divided by 2. You need to memorize all of these. You need to memorize all of those formulas. I will not give them to you on a quiz or on the test. You need to memorize them. Okay, we're going to stop here for today. Your assignment, and there should be a little bit of time left over, your assignment is to do section 3.4, day 1. And I think you will be very happy with this assignment because it's only 1 page long. One side of 1 page. So you can get this done pretty quickly if you are smart and done what I've asked you to do since day 1 in here, which is to print out the homework ahead of time. You can go take out that homework and you can do it right now. If you haven't printed it out, then, oh gosh, I don't know, you're out of luck. I will see you tomorrow. Thanks. Have a good afternoon. Bye.